In this video, we're going to be introducing a family of chemicals called bases, which actually behave oppositely to acids when they are added to water. We're going to be using the base sodium hydroxide as an example of bases, as it shares most of the common characteristics with the bases that we're going to be seeing in this unit. Now, unlike acids, which are almost exclusively covalent compounds, we can see that sodium hydroxide is clearly an ionic compound containing a metal ion and an OH- ion, which is the polyatomic ion hydroxide, or OH-, as we see here. So these are, not surprisingly, what we call ionic bases, because again, they form because of the positive-negative attraction that occurs in all ionic compounds. And indeed, we can come up with the formulas for multiple ionic bases by simply taking different metals and combining them with the appropriate number of hydroxide ions. For example, another common metallic base is potassium hydroxide. Because potassium has a positive 1 charge, it will only have 1 hydroxide ion. Another example would be magnesium hydroxide, but because magnesium has a positive 2 charge, that means that it needs 2 hydroxide for a negative 2 charge to cancel out the positive charge. Another example would be aluminum hydroxide, which again, if we follow the pattern, aluminum has a positive 3 charge, meaning that it requires 3 hydroxide in order to cancel out the positive 3 charge. And of course, we can have transition metals with multivalent charges in the form of bases. So for example, we can make copper 2 hydroxide here. So if copper has a positive 2 charge, it's going to need 2 hydroxides to balance the charge like this. And all of these all serve as examples of ionic bases because, again, they form using a metal cation paired with the appropriate number of hydroxide anions. However, this doesn't actually describe all bases. For example, we can see probably one of the most famous bases, one of the ones that's actually used in cleaning products like bleach, is this compound that we call ammonia, and from its structure we can see that it's actually a covalent compound, and many covalent compounds that contain nitrogen in key locations are examples of organic bases. Now, unlike ionic bases, we can see that ammonia doesn't actually contain the OH- ion, but instead, once covalent bases are added to water, they actually react with water in order to produce OH-, which is a chemical reaction that you will explore in detail in Chemistry 11. Now, just like with acids, there are also organic varieties of bases, meaning that they contain carbon as their central element, as we can see here. And just like with other covalent bases, we can see that they also have nitrogen that is a key part of their structure. And just like with non-organic but still covalent bases, they do not actually have OH- as part of their structure, but instead react with water when they are added to water in order to produce OH-, just like ammonia that we see above. Now, if we stick to ionic bases, which are the bases that we're going to be focusing on exclusively, when bases are added to water, they undergo what we call the process of dissociation, which simply means that when they are put into water, water causes them to dissolve. And assuming that we have enough water to dissolve the base, which happens very similarly to the way salt dissolves, the water will actually surround the structure of the ionic base and separate the two ions once the base is surrounded by water. So what this means is that the water is actually going to pull apart the OH minus ion, the ion that makes it a base, from the metal ion that we see here. And once the metal ion and the hydroxide ion have been separated from each other, the base is considered dissolved in water, and as long as a solution of water contains an OH minus ion, the solution is considered to be basic, meaning that it contains bases. Now, unlike acids, which very, very commonly are used in human cuisine, most bases are actually very, very deadly poisons. For example, anyone who has seen any of the memes associated with drinking bleach know that this is a terrible idea, as bleach not only tastes abominably horrible, but is also a very deadly poison. In fact, humans have developed an adaptation to protect us from drinking too much base, as most bases have a bitter taste associated with them, and at least for me, I find bitter tasting food to be very, very unpleasant and have the instinct to spit it out. However, there are a few exceptions to this, namely coffee and tea. And for anybody that knows the active ingredient in coffee and tea that prevents you from feeling tired, this is actually a chemical that's called caffeine, which is actually an example of an organic base. And for people that find that strong tea and black coffee have a very bitter taste to it, what you are tasting is the caffeine within the coffee or tea. Now, one of the best examples of a base that we work with, but certainly that we don't consume in our daily lives, is soap. Now, this also highlights another characteristic of bases in that most people find them to have a very slippery texture. For example, the bar of soap that we can see forming suds like this, and also bleach, if you get it on your hands, tends to have a very slippery texture as well. This concludes our introduction to bases. In the next video, what we're going to look at is the measurement system that is used by chemists in order to measure how much acid or how much base is present within a specific liquid.